Okay, buckle up. What happened?
Any questions?
Okay. Okay. Small angle neutron scattering sands. We all really enjoyed this experiment, and we really hope to share our joy with you today. So a little bit about what we're going to talk about. It's a little bit hard to read. We deuterated our bullets, so there's a better contrast. So we're going to start off, talk about comic sands, and talk about the beamline, talk about our experiment, and then we're going to really get into how we fit the data and what the results mean. So take it away, Julia.
Okay, this is a comic. This is SANS. SANS is small angle neutron scattering. It's an elastic neutron scattering technique where when we collect at small angles, we can study mesoscale structures because larger structures allow us to, because larger structures scatter at smaller angles and from SANS data, we can study the size, shape, molecular weight of our materials, and as well as interactions between particles, their distances, and self-assembled structures. It's a very powerful tool for studying disordered bulk materials in solid and solution phases. So as you can see, a monochromatic, a monochromatic incident beam hits our sample, and then we collect it at a longer distance in order to get the smaller angles. The intensity that we collect is the Fourier transform of the scattering length density distribution, and it's also related to a structure factor and a form factor that in the interest of time I will not be telling you about. And so the intensity is also dependent on this delta rho, which is the scattering length density contrast. And it's the reason why SANS is such a powerful technique because the scattering length density is dependent on the nucleus, and it allows us to distinguish between isotopes. So using SANS, we can probe length scales, like I said, mesoscale, so 0.5 to 100 nanometers using an angle of 0.5 to 5 degrees.
So the beamline, there they are. They're really big. These are the SANSes. There are two of them, GP, general purpose, and bio. And the incident beam comes from back there. And in the background, that's the GP SANS. In the foreground, that's the bio SANS. And in the foreground, that's Dr. Vanke. He helped us out. He was really nice. And that's a detector you can look down through in the window. That is about 40 meters long, and as Julia said, need that long distance between sample and detector to help catch those small angles. And the difference between the GP and the bio is that the GP is oversubscribed by a factor of 10, inside tip that we got. So if you want to use this in the future, we recommend that you try to sign up for the bio SANS.
Okay, so now that you guys know exactly how the instrument works, we're going to go into the exact materials that we used. So pretty much we looked at the assembly of this tri-block copolymer shown here. So there we go. So it has a central block of PPO, or polypropylene oxide, surrounded by two blocks of polyethylene oxide, or PEO. And the central block, PEO, has temperature responsive properties where above temperatures of about 15 degrees C, the PEO is no longer soluble in water. So really what we expect to observe here is that we increase temperature above approximately 15 degrees C. This PPO block will want to separate away from the water. And to do this, the central block will essentially bend inward away from the water in the surrounding environment so that it forms a central core in a micelle with the two PEO blocks extending out from there, and essentially, so the PEO blocks rather are in the water, and the PPO is essentially no longer surrounded by water molecules. So, sort of getting into the experiment that we did, Pretty much with this tri-block copolymer, what we did is we collected SANS data at a range of temperatures, both below that expected transition point of around 15 degrees C, as well as many temperatures above this. And we fit models to the observed scattering intensity. Now, what we did is that because we ran these experiments at relatively dilute conditions at about 7 weight percent in D2O, so what we expected to see, aside from the great contrast, because we're doing this in D2O versus all the hydrogens present on the polymer chains, really what we're trying to do is fit form factors to these models, or form factors to the observed scattering intensity. Because this is so dilute in solution, we're pretty much ignoring the effects of any correlation between molecules because, again, they're so dilute and they can't really see the effects of each other. And what we're trying to find in looking at all this range of temperatures is first trying to find a point of this critical micelle temperature, so this point at which micelles begin to form as opposed to just the polymer chains behaving as, for example, a coil or a hard sphere. And also by looking at temperatures well above this transition point, we want to see in how any changes in like the spatial properties of these micelles, so how the size of the core and the corona change, as well as other properties. So for the temperatures, or rather for the form factor models that we mainly use to try to fit the data for the low temperature samples, there were two models that we were trying to distinguish between. One is this random Gaussian coil shown up top here, which has three main parameters in it. One which includes the radius of gyration of the coil, as well as a parameter that adjusts the amplitude of the shape that we fit to the curve, as well as an additional parameter for background. Now there's another potential conformation that these polymers can take on, and this would be a hard sphere. Again, it's another 3-parameter model, the same 3 as the coil. And if you look at these two general images here, there's not that much of a difference. They're actually the same image. This one just has a circle around it. So really, what we're looking at here is not only can we fit either of these to the data, but can we distinguish between these and within the fits?
Okay, so as Justin mentioned earlier, when we raise the temperature, our tribulate copolymer phase separates so that our PPO block forms a core, and then we have the corona of our PEO segments. So we needed to use the Perkasiewicz model, which is sort of a core shell model, to best describe a PPO center with a PEO corona. And so this is that model. We don't really need to get into that too much, but it adds in a few more factors. So Kelly's going to talk about the data.
All right, here we can see by our low temperature data, we can see that we can't observe any characteristic peaks in this data, but we were able to fit it to a coil model. And as Dale Schaefer mentioned last week, we can fit an elephant into this data. So when we move to higher temperatures, we can see that we do see these characteristic peaks where we see different shapes. So we did fit this to the core shell model, the Perkasiewicz model, in order to actually observe these at higher temperatures. As we can see in our actual results, as you increase from low temperatures, as you have, when you have low temperatures, these molecules are by themselves. They don't aggregate in any sort of shapes that we can see. However, as we do increase the temperature, as Justin mentioned, those hydrophobic blocks in the middle will want to be away from the water. So the PEG blocks on the outside blocks will allow this to form a corona, while the core will be made of that hydrophobic PPO block. So we can see that aggregation starts to occur a little bit lower than 30 degrees. And as we increase temperature, the aggregation number, this is how many individual polymer chains come together and actually form that aggregate. They start to increase while the corona and core radius actually stays relatively constant once it starts to aggregate. We can also see that as temperatures increase, the volume fraction of the micelles in solution stays relatively constant while the penetration parameter increases. So this means that this describes the amount of hydrophilic block that's either in the core or hydrophobic block that's in the corona. So next.
All right, so we did this fitting using Igor and a module developed by the Beamline scientists to help with this fitting. One of the things is Beamline, or general scattering users, when we try and look at our data and fit it with a model, we need to worry about error and error propagation. So during our discussion of this experiment, we talked about error analysis and when you can use just the covariances given to you from the fit. For the simple model, the Gaussian coil or the hard sphere, those are simple enough that the error that the model gives you is adequate. But when you go to something like 2 minutes, okay. When you go to something like the Perkasiewicz model, where you have a bunch of parameters, the estimated error returned to you from that fit is going to be artificially small and potentially inaccurate. So here we're just going to quickly go over error analysis as described by Venki, the Beamline scientist. What you want to do is generate a chi-square distribution for a given parameter. So you set that parameter at a bunch of different values, let everything else vary, and look at how your chi-squared varies. We didn't actually have time to do this for our data, so I've simulated these results shown here. So for a given model, you look at the number of degrees of freedom of that model. You can do a statistical test and basically get a confidence interval on your chi-squared. So graphically, you have some multiplication factor, and then where this factor intersects your chi-squared distribution, you get the confidence interval on whatever parameter you're looking at. So illustrated here would be two different models and a given chi-squared confidence interval and the resulting error bars in each. And so going back to our data, if we had some error that would be 5% in either direction, we would be confident of our trend. So here's the core radius as a function of temperature, and you can see it continually increases. This would be a good result, and we could be confident in our model. But if we fit it with something like an elephant form factor, we may get something that looks like this, where we actually have no trend, and our results are inconclusive. So Dale Schaefer says you can fit an elephant, and so do I. The procedure for this in depth is detailed in this book, Data Reduction and Error Analysis for the Physical Sciences by Philip Bevington and Keith Robinson.
And to conclude, here's a picture of a carrot with a ring and another picture you've never seen before. And it's spinning. Cool. It's going to take a while. And thank you, everyone, for sitting through this. And we would also like to thank our favorite cats and dogs and minerals. That's it.
So I'm not sure if I was reading this plot wrong, but Pete, when you were talking about kind of adding more and more parameters, and you showed your error actually increasing, and I guess first off, is that, like, after a certain point your error increases, is that true is that what you intended to say with this?
No. So for example, if this is our core radius, it'd be, say, 30 angstroms or 30 nanometers. You set that given value, so you could set it at 25 or 35, let all the other parameters vary, and look at what the chi-squared of that fit gives you. If you have some model that can fit the data no matter what this parameter is, you'll have a very shallow looking distribution, and so you're going to have really large error bars. If you have a model where your chi-squared is very sensitive to that parameter value, you can be more confident in that value that the fit gives you. Charles?
Some more general questions, not the technique, but how do you do like internal balance? Like, do you have a calibration for the system? How do you calibrate like the size of this particle instead?
Well, that's why you fit it to a model. We don't have an internal calibration. You don't have an internal calibration for these measurements, so you have to fit it to a model after you acquire the data.
But there are standards that you can use to determine the Q value at a given sample to detector distance.
Yeah.
How do you know the error bars from your data points?
For
Like in the no your
In the
raw
actual data.
Oh, nice.
so yeah, so the real data, we didn't have time to do that, but this is the procedure you would use in order to give the error bars. This has been published previously, so it's significant.
On the well-run error analysis, what key value would you use, or were the scientists using associated with the given chi-squared value to define those error bars?
So you look at the model and
It's the number of parameters.
yeah, so it's based on the number of parameters. So the more parameters you have, you're going to have a larger multiplication factor for your confidence interval.
What key value though?
I don't know. We didn't go into that.
How do you determine the aggregation number of the micelle? Given you show that you determine the RG of the micelle, which makes sense. So how do you determine the R of the corona? You got
It's all contained within the Perkins-Yavik model. Sorry, what?
the aggregation number?
The aggregation, yeah, that was also determined from the fit and the models that we or the fit parameters.
I don't know anything about soft matter. If I had to review things, what would you tell me? Why do I care about PPL, tribot?
I can feel this. It's also known as pluronic, and it's used in contact lenses to shuttle impurities out of your contact lenses. It needs to form the micelles in order to do that.
So you can make better contact lenses?
All materials.
That's exactly what we did, yes.